Now, field due to uniformly charged thin spherical cell. Suppose here we have uniformly charged thin spherical shell with surface charge density sigma having radius equal to capital R. And suppose total amount of charge residing on the spherical shell, that is Q. Here we have to calculate the electric field outside the spherical shell as well as inside the spherical shell. Suppose first we consider any point outside the spherical shell. So here consider the Gaussian surface. Which one is a spherical one passing through that point where we want to find the electric field. So see, as shown in this figure, the Gaussian surface under consideration, that is this one with radius equal to small r, where small r is greater than r. It implies that now we are considering the point which is outside the charged spherical shell. And the point where we want to find the electric field, that is on the spherical Gaussian surface. The center of the spherical Gaussian surface is coinciding with the center of spherical shell. Now, flux passing through this particular spherical Gaussian surface, that is, as per definition, we can write sigma E dot delta S. Delta S, that is infinitesimal small element on the Gaussian surface, and electric field at the position of this element, that is E, but electric field that is radially outward. Here sigma is greater than 0. So electric field and this area vector both are radially outward, so are in the same direction, so theta equal to 0. So cos theta, that is cos 0, that is 1. So we can write this sigma E dot delta S, that is E sigma delta S. E, that will be same one because each and every point on this particular Gaussian surface, that is at the same distance small r from the center. So due to this spherical symmetry, the field will be same one at each and every point. So we can write now flux passing through this Gaussian surface, that is E sigma delta S. But as per Gauss's theorem, that is Q upon epsilon 0. So we can write E sigma delta S, that is Q upon epsilon 0. So E sigma delta S, that will give you the total spherical surface area of the Gaussian surface, that is 4 pi r square, that is equal to Q upon epsilon 0. So we can write E, that is equal to Q upon 4 pi epsilon 0 r square. Or in vector form, we can write E, that is Q upon 4 pi epsilon 0 r square into r caret. Now see this equation. This one is equation exactly like the electric field due to a point charge Q at a point which one is situated at distance r from the charge. So here we can understand this thing. This entire spherical charge distribution behave like a point charge concentrated at the center of the spherical shell for any point which one is outside the shell. Clear to all of you? Now Q, that is the total charge residing on this particular spherical shell. So if you want to write the answer in terms of surface charge density, then total charge, that is charge per unit area into total area. So sigma into 4 pi capital R square, that is your Q, upon 4 pi epsilon 0 small r square as it is. So 4 pi cancel. So electric field, that is sigma r square upon epsilon 0 small r. square. So you can write the equation of the electric field in terms of charge residing on the cell like this, and then electric field in terms of surface charge density of the spherical shell as this one. Clear to all of you? Now think about the electric field at any point inside the spherical shell. So here again, consider the spherical Gaussian surface having radius equal to r dash, for which the center of the Gaussian surface is coinciding with the center of spherical shell. And r dash is less than capital R. It implies that this spherical Gaussian surface is inside the charged cell. And now we want to find the field at any point on the surface of this Gaussian surface, each and every point that is at the same distance r dash from the center. So we can write flux phi, that is sigma E dot delta S, that is equal to, as per Gauss's theorem, Q upon epsilon 0. But see here, Q, that is the charge enclosed by Gaussian surface. Here, entire charge is outside the Gaussian surface. So net charge enclosed by the surface is 0. So here we have to take Q equal to 0, this one. So if we take Q equal to 0, then E equal to 0. It implies that inside the charged spherical shell at any point, the electric field is 0. Clear to all of you?